In this problem, we're asked to use separation of variables to find a general solution of a first-order differential equation, and then we're asked to apply an initial condition in order to nail down a particular solution. So let's do the separation of variables thing. I'm going to rewrite the differential equation, but with the derivative in Leibniz notation. And then I move all the y dependence to the left-hand side, so dy over y, and all the x dependence to the right-hand side, so I have x minus 2 dx. And separation of variables works by just saying, okay, now I can just integrate both sides. And an integral of dy over y is going to be a natural log absolute value y. And the integral of x minus 2 dx is 1/2 x squared minus 2x plus an arbitrary constant. Then I go about solving for y. So I'm going to raise to the e on the right-hand side and have absolute value of y equals e to the 1/2 x squared minus 2x plus c. I could write that as e to the c, e to the 1/2 x squared minus 2x. And they go, okay, well, if c is an arbitrary constant, then e to the c must be some other arbitrary constant. There's a subtlety here, however. The e to the c is always a positive number, so this c right here must be positive. And we're eventually going to be able to relax that restriction. So it has to do with the absolute value bars on y. If y is positive, the absolute value leaves it alone, and I get this solution. And if y is negative, the absolute value multiplies it by -1, and I'm going to move the -1 to the other side. And I can take these two things together. Remember, c is positive, and I can say I get solutions where y is either a positive arbitrary constant times this exponential stuff, or I get solutions where y is a negative arbitrary constant times this exponential stuff. Well, there's an easy way to say that all at once. Y is equal to some arbitrary constant that could be positive or negative times all this exponential stuff. So there's our general solution. Now, in practice, I normally just blow off the absolute value bars on the y, and you end up with the right answer by doing that. I just like to occasionally explain what's going on underneath. So now I'm going to take my general solution and apply this initial condition. It says when x is 0, y is 1. So replace y with 1. Replace all the x's with zeros, and when I do that, I get e to the 0, which is just 1, and I end up with c equals 1. So the particular solution is found by just replacing c with 1. And like all particular solutions, this function will satisfy the differential equation. So if you differentiate it, you get the original function y multiplied by x minus 2. But it also passes through the point given by the initial condition. So when x is 0, y is equal to 1.